Main memory is where programs and data are kept when the processor is actively using them. When programs and data become active, they are copied from secondary memory into main memory where the processor can interact with them. A copy remains in secondary memory. Main memory. Obviously, memory access and memory management are very important part of modern computer operations. Every instruction has to be fetched from memory before it can be executed, and most instructions involve retrieving data from memory or storing data in memory or both. The advent of multitasking operating systems compound the complexity of memory management because as processes are swapped in and out of the CPU, so must their code and data be swapped in and out of memory, all at high speeds and without interfering with any other processes. Shared memory, virtual memory, the classification of memory as read-only versus read-write, and concepts like copy on write, forking all further complicate the issue. Let's proceed to basic hardware. It should be noted that the memory chip's point of view, all memory accesses are equivalent. The memory hardware doesn't know what a particular part of memory is being used for, nor does it care. It is almost true of the operating system as well, although not entirely. The CPU can only access its registers and main memory. It cannot, for example, make direct access to hard drive, so any data stored there must first be transferred into the main memory chips before the CPU can work with it. Device drivers communicate with their hardware via interrupts and memory access, sending short instructions, for example, to transfer data from the hard drive to a specified location in main memory. The desk controller monitors the bus for such instructions, transfer the data, and then notifies the CPU that the data is there with another interrupt, but the CPU never gets direct access to the desk. Memory access to registers are very fast. Memory access to main uh, Memory access to registers are very fast, generally one clock tick, and the CPU may be able to execute more than one machine instruction per clock tick. Memory access to main memory are comparatively slow and may take a number of clock ticks to complete. This would require interrelable waiting by the CPU if it weren't not for an intermediary fast memory cache built into most modern CPU. The basic idea of the cache is to transfer chunk of memory at a time from the main memory to the cache and then access individual memory location one at a time from the cache. User processes must be restricted so that they only access memory location that belong to particular access. This is usually implemented using a base register and a limit register for each process, as shown in the figure 8 and figure 8.1 and figure 8.2. Every memory access made by a user process is checked against these two registers. And if a memory access is attempted outside the valid range, then a fatal error is generated. The operating system obviously has access to all existing memory locations, as this is necessary to swap users' code and data in and out of memory. It should also be obvious that changing the contents of the base and limit registers is a privileged activity allowed only to the operating system kernel. So from operating system, ang base is 300,040 to ang limit is 120,900. And then sa kaning trapped operating system monitor addressing error. Sa figure 8.2, hardware address protection with base and limit registers. CPU to address and to CPU address to base and to base plus limit and then to memory. So let's proceed to address binding. User programs typically refers to memory addresses with symbolic names such as I, count, and average temperature. These symbolic names must be mapped or bound to physical memory addresses, which typically occurs in several stages. So the first stage is compile time. If it is known at compile time, where a program will reside in physical memory, then absolute code can be generated by the compiler, containing an actual physical addresses. However, if the load address changes at some later time, then the program will have to be recompiled. DOS.com programs use compile type binding, and then the next stage is load time. If the location at which a program will be loaded is not known by at compile time, then compiler must generate relocatable code which references addresses relative to the start of the program. If that starting addresses changes, then the program must be reloaded but not recompiled. And then the next or last stage is execution time. If a program can be moved around in memory during the course of its execution, then binding must be delayed until execution time. This requires special hardware, and is the method implemented by most modern operating systems. In Figure 8.3 shows the various stages of the binding processes and the units involved in each stage. So, source program is under masulod siya sa compiler or assembler. Una na siya ang compile time. And then, next is object module, and other object modules is ato siya sa linkage editor. And then, the load module, and then the system library is proceed siya sa loader. So, from linkage editor to loader is na siya ang load time. And then, ang dynamically loaded system library is padulong siya sa in-memory binary memory image. Mauna ni siya ang execution time or runtime. And then, let's proceed to logical versus physical address space. The address generated by the CPU is logical address, whereas the address actually seen by memory hardware is a physical address. And then addresses bound at compile time or load time have identical logical and physical addresses. The address created at execution time, however, have a different logical and physical addresses. In this case, the logical addresses is also known as virtual address. And then the two terms are used interchangeably by our text. The set of all logical addresses used by a program compose the logical address space, and the set of all corresponding physical addresses composes the physical address space. The runtime mapping of logical to physical address is handled by the Memory Management Unit or MMU. The MMU can take on many forms. One of the simplest is a modification of the base register scheme described earlier. The base register is now termed a relocation register, whose value is added to every memory request at the hardware level. Note that the user programs never see physical addresses. User programs work entirely in logical address space, and any memory references or manipulations are done using purely logical addresses. Only when the address gets sent to the physical memory chips is the physical memory address generated. So, CPU to logical address, and then to relocation register to physical address padulong sa memory. O na siya ang MMU or Memory Management Unit. Then, mag-proceed sa dynamic loading. Rather than loading an entire program into memory at once, dynamic loading loads up each routine as it is called. The advantage is that unused routine needs never be loaded, reducing total memory usage and generating faster program startup times. The downside is the added complexity and the overhead of checking to see if a routine is loaded every time is it is called, and then loading it up if it is not already loaded. And then proceed to dynamic linking and shared libraries. With static linking, library modules get fully included in executable modules, wasting both disk space and main memory usage. Because every program that included a certain routine from the library would have to have their own copy of that routine linked into their executable code. With, the, with dynamic linking, however, only a stub is linked into the executable module containing references to the actual library module linked in at runtime. This method saves the disk space. So, kaning method is mag-save siya og space because the library routine do not need to be fully included in the executable modules, only the stubs. We will also learn that if the code section of the library routines is reentrant, meaning it does not modify the code while it runs, making it safe to re-enter it. Then main memory can be saved by loading only one copy of dynamically linked routine into memory and sharing the code amongst all processes that are concurrently using it. Each process would have their own copy of the data section of the routines, but that may be small relative to the code segment. Obviously, the operating system must manage shared routines in memory. An added benefit of dynamically linked libraries, or DLL, also known as shared libraries or shared objects in Unix system or UNIX systems, involves easy upgrades and updates. When a program uses a routine from a standard library and the routine changes, then the program must be rebuilt or relinked in order to incorporate the changes. However, if the DLL are used, then as long as the stub doesn't change, the program can be updated merely by loading new versions of the DLL onto the system. Version information is maintained in both the program and the DLL so that a program can specify a particular version of the DLL and if necessary. In practice, the first time a program calls a DLL routine, the stub will recognize the fact and will replace itself in the actual routine from the DLL library. Further calls the same routine will access the routine directly and not incur the overhead of the stub access. And then, mag-proceed na ta sa swapping. A process must be loaded into memory in order to execute. If there is not enough memory available to keep all running processes in memory at the same time, then some processes who are not currently using the CPU may have their memory swapped out to a fast local disk called backing store. Ang first type or what is it is standard swapping. If compile time or load time address binding is used, then processes must be swapped back into the same memory location from which they were swapped out. If execution time binding is used, then the process can be swapped back to any available location. Swapping is a very slow process compared to the other operations. For example, if a user process occupied 10 MB and the transfer rate for the backing store were 40 MB per second, then it would take 1/4 second or 250 milliseconds just to do the data transfer. Adding in latency lag of 8 milliseconds and ignoring head seek time the, for the moment, and further recognizing the swapping involves moving old data out as well as new data in. The overall transfer time required for the swap is 512 millisecond or over a half second. For efficient processor, scheduling and CPU time slice should be significantly longer than this lost transfer time. To reduce swapping transfer overhead, it is desired to transfer as little information as possible, which requires that system know how much memory a process is using and opposed to how much it might use. Programmers can help with this by freeing up dynamic memory and they are no longer using. It is important to swap processes out of memory only when they are idle or more to the point only where there are no pending I/O operations. Otherwise, the pending I/O operation could write into the wrong process's memory space. The solution is to either swap only totally one process or do I/O operations only into and out of operating system buffers, which are then transferred to or from processes main memory as a second step. Most modern operating systems no longer use swapping because it is too slow and there are fast alternatives available or the paging. However, the UNIX systems or Unix systems will still invoke swapping if the system gets extremely full and then discontinue swapping when the load reduces again. The Windows 3.1 would use a modification ver Next nga, part sa swapping is swapping on mobile systems or new section in ninth edition. Swapping is typically not supported on mobile platforms for several reasons. First is mobile devices typically use flash memory in place or more spacious hard drives for persistent storage, so there is not as much space available. And then flash memory can only be written to a limited number of times before it becomes unreliable. And then the third is the bandwidth to flash memory is also lower. Apple's iOS asks applications to voluntarily free up memory. Read only data code is simply removed and reloaded later if needed. Modified data, the stock, is never removed, but apps that fail to free up sufficient memory can be removed by the OS. Android follows a similar strategy prior to terminating a process. Android writes its application state to flash memory for quick restarting. Ang next is contiguous memory allocation. One approach to memory management is to load each processes into a contiguous space. The operating system is allocated space first, usually at either low or high memory locations, and then the remaining available memory is allocated to process as needed. The operating system is usually loaded low because that is where the interrupt triggers are located. But not only older system part of the operating system was loaded high to make more room in low memory within the 640K per year for users process. Under it is memory protection, was memory mapping and protection. The system shown in figure 8 below allows protection against user programs accessing areas that they should not allow programs to be relocated to different memory starting addresses as needed and allows the memory space devoted to the OS to grow or shrink dynamically as needs change. From CPU to logical address to limit register. CPU, logical address, and then to limit registers, then to relocation registers, and then physical addresses to memory. That is a trap addressing error. Then, mag-proceed ka sa memory allocation. One method of allocating contiguous memory is to divide all available memory into equal size pat- partitions and to assign each process to their own partitions. This restricts both the number of the simultaneous processes and maximum size of each process and is no longer used. An alternative approach is to keep a list of unused free memory blocks or holes and to find a hole of a suitable size whenever a process needs to be loaded into memory. There are many different strategies for finding the best allocation of memory to process, including the three most common discussed. First feat is search the list of holes until it is not found that is big enough to satisfy the request and assign a portion of that hole to that process. Whatever fraction of the hole not needed by the request is left on the free list as a smaller hole. Subsequent requests may start looking either from the beginning of the list or from the point at which this search ended. This is ang best fit or ang ikaduha is allocate the smallest hole that is big enough to satisfy that request. This saves large holes for another process requests that may need them later. But the resulting unused portions of holes may be too small to be any use and will therefore be wasted. Keeping the free list sorted can speed up the process of finding the right hole. And then the third is the worst fit. Allocate the large hole available, thereby increasing the likelihood that the remaining portion will be unusable for satisfying future requests. Simulations show that either first or best fit are better than worst in terms of both time and storage utilization. First and best fits are about equal in terms of storage utilization, but first fit is faster. And then, mag-proceed na sa fragmentation. All the memory allocation strategies suffer from external fragmentation. Though first and best fits experience the problems more so than worst fit. External fragmentation means that available memory is broken into lots of little pieces, none of which is big enough to satisfy the next memory requirement, although the sum total could. The amount of memory lost to fragmentation may vary with algorithm, usage pattern, and some design decisions such as which end to a hollow allocate and which and to save on the free list. Statistical analysis of first fit, for example, shows that for n blocks of allocated memory, another zero point 0.5 will be lost to the fragmentation. Internal fragmentation also occurs with all memory allocation strategies. This is caused by the fact that memory is allocated in blocks of a fixed size, whereas the actual memory needed will rarely be that exact size. For a random distribution of memory requests, on the average, one half block will be wasted per memory request. Because of the average, the last allocated block will be only half full. So, note that the same effect happens with hard drives, and that modern hardware gives us increasingly larger drives and memory at the expense of ever larger block sizes, which translate to more memory loss to internal fragmentation. Some systems use variable size blocks to minimize losses due to internal fragmentation. If the program in memory are relocatable using execution time address binding, then the external fragmentation problem can be reduced via compaction, moving all processes down to one end of physical memory. This only involves updating the relocation register for each process, as all internal work is done using logical addresses. Another solution, as we will see in upcoming sections, is to allow processes to use non-contiguous blocks of physical memory with a separate relocation register for each block. And then now we are going to proceed sa segmentation. Under this is ang basic method. Most users or programmers do not think of their programs as existing in one continuous linear address space. Rather, they tend to think of their memory in multiple segments, each dedicated to a particular use, such as code, data, the stack, the heap, or etc. Memory segmentation supports this view by providing address with a segment number or map to a segment base address and offset from beginning of that segment. For example, a C compiler might generate five segments for the user code, library code, global or static variables, the stack, the heap as shown in figure 8.7. So, logical address. Figure 8.7 is programmer's view of a program. Ang sulod ana is mao ni ang kuan subroutine, ang stack, ang symbol table, ang main memory, and then the other one. And then sa under gihapon sa segmentation is ang segmentation hardware. This is a segment table map segment offset addresses to physical addresses and simultaneously checks for invalid addresses using a system similar to the page tables and relocation-based registers discussed previously. Note that at this point in the discussion of segmentation, each segment is kept in contiguous memory and may be of different sizes, but that segmentation can also be combined with paging as well, as we shall see shortly. So from CPU, ang S is under the S is ang limit o ang base, which is the segment table, and then ang D is less than sa kuan sa manage table sa katong segmentation hardware nga top addressing error. And then ang isa pod ka table is gikan siya sa katong logical address space kanang masulod ato, tas ang segment table na dayon ang limit is kung sa 0, ang limit is 1,000. Sa base naman is 1,400. Kung ay isa, ang limit is 400 and then ang base is 6,300. Then pag duha, 400 ang limit and then 4,300 ang and then number 3. 1,100 ang limit and then ang base is 3,200. Ang upat is 1,000 ang limit and then 4,700 ang base. And then mag-proceed na rin sa next under main memory.
Paging. Paging is a memory management scheme that allows processes' physical memory to be discontinuous and which eliminates the problem with fragmentation by allocating memory in equal size blocks known as pages. Paging eliminates most of the problems of the other methods discussed previously and is the predominant memory management technique used today. Basic method. The basic idea behind paging is to divide physical memory into a number of equal size blocks called frames, and to divide a program's logical memory space into blocks of the same size called pages. Any page from any process can be placed into any available frame. The page table is used to look up what frame a particular page is stored in at the moment. In the following example, for instance, page 2 of the program's logical memory is currently stored in frame 3 of physical memory. A logical address consists of two parts: a page number in which addresses resides, and an offset from the beginning of that page. The page table maps the page number to a frame number to yield a physical address which also has two parts: the frame number and the number of bits of the offset determines the size of each frame. Page numbers. Frame numbers and frame sizes are determined by the architecture but are typically powers of two, allowing addresses to be split at a certain number of bytes. For example, if the logical address size is 2m and the page size is 2n, in the higher order m to n bits of a logical address designate the page number and the remaining n bits represent the offset. Note also that the number of bits in the page number and the number of bits in the frame number do not have to be identical. The former determines the address page of the logical address space, and the latter relates to physical address space. DOS used to an addressing scheme with 16 bytes from frame numbers and 16-byte offsets on hardware that only supported 24-byte hardware addresses. The result was a resolution of starting frame addresses finer than the size of a single frame, and multiple frame offset combination that mapped to the same physical hardware address. Consider the following microexample in which a process that 16 bytes of logical memory map in 4-byte pages in 32 bytes of physical memory. Presumably some other processes would be consuming the remaining 16 bytes of physical memory. Note that paging is like having a table of relocation registers, one of each page of the logical memory. There is no external fragmentation with paging. All blocks of physical memory are used, and there are no gaps in between and no problems with finding the right sized hole for a particular chunk of memory. There is, however, internal fragmentation. Memory is allocated in chunks the size of a page, and on the average, the last page will only be half full, wasting on the average half a page of memory per process. Possibly more, if processes keep their code and data in separate pages. Larger page size weighs more memory, but are more efficient in terms of overhead. Modern trends have been to increase page sizes, and some systems even have multiple sizes pages to try and make the best of both worlds. Page table entries, frame numbers, are typically 32-byte numbers, allowing access to 230 physical page frames. If those frames are 4 KB in size each, that translates to 16 TB of addressable physical memory. 32 plus 12 equals 44 bytes of physical addresses space. When a process requests memory, example, when its code is loaded in from disk, free frames are allocated from a free frame list and inserted into the process's page table. Processes are blocked from accessing anyone else's memory because all their memory requests are mapped through their page table. There is no way for them to generate address that maps into any other process's memory space. The operating system must keep track of each individual process's page table, updating it whenever the process pages get moved in and out of memory, and applying the correct page table when processing system calls for a particular process. These all increase the overhead involved with swapping processes in and out of the CPU. The currently active page table must be updated to reflect the process that is currently running. Hardware support. Page looks up must be done for every moment referenced, and whenever a process gets swapped in or out of the CPU, each page table must be swapped in and out too, along with instruction registers, example, etc. It is therefore appropriate to provide hardware support for the operation in order to make it as fast as possible and to make process switches as fast as possible also. One option is to use a set of registers for the page table. For example, the DEC PDP-11 use 16-byte addressing and 8 KB pages, resulting in only 8 pages per process. It takes 13 bytes to address 8 KB of offset, leaving only 3 bytes to define a page number. An alternate option is to store that page table in main memory and to use a single register called the page table base register or PTBR to record where in memory the page table is located. Process switching is fast because only the single register needs to be changed. However, memory access got half as fast because every memory access now requires two memory access. One to fetch the frame number from memory and then another one to access the desired memory location. The solution to this problem is to use a very special high-speed memory device called the Translation Lock Aside Buffer or TLB. The benefit of the TLB is that it can search an entire table for a K value in parallel, and if it is found anywhere in the table, then the corresponding lookup value is returned. The TLB is very expensive, however, and therefore very small, not large enough to hold the entire page table. It is therefore used as a catchy device. Addresses are first checked against the TLB, and if the info is not there, a TLB missed. Then the frame is looked up from main memory and the TLB is updated. If the TLB is full, then replacement strategies range from least recently used LRU to random. Some TLBs allow some entries to be wired down, which means that they cannot be removed from the TLB. Typically, these would be kernel frames. Some TLBs store address space identifiers or assets to keep track of which process owns a particular entry in the TLB. This allows entries from multiple processes to be stored simultaneously in the TLB without granting one process access to some other process's memory location. Without this feature, without granting one process access, without this feature, the TLB has to be flushed clean with every process switch. The percentage of time that the desired information is found in the TLB is the term that hit ratio. 8th edition version, for example, suppose that it takes 100 nanoseconds to access main memory and only 20 nanoseconds to search the TLB. So a TLB hit takes 120 nanoseconds total. 20 to find the frame number and the another 100 to get that data. And a TLB miss takes 220. You need to search the TLB 100 to get the frames number and then another 100 to get the data. So with an 80% TLB hit ratio, the average memory access time would be 0.80 to 120 plus 0.20 to 20 equals 140 nanoseconds. For a 40% slowdown to get the frame number, a 98% hit rate would yield 122 nanoseconds average access time. We should verify this for a 22% slowdown. 9th edition version. The 9th edition ignores the 20 nanoseconds required to search the TLB, yielding 0.80 to 100 plus 0.20 to 200 equals 120 nanoseconds. For a 20% slowdown to get the frame number, a 99% hit rate would yield 101 nanoseconds average access time. You should verify this for a 1% slowdown. Protection. The page table can also help protect process from accessing memory that they shouldn't, or their own memory in ways that they didn't shouldn't. A bit of bits can be added to the page table plus of a page as read write, read only, read write, execute, or some combination of these sorts of things. Then each memory reference can be checked to ensure it accessing memory in the appropriate mode. Valid or invalid bytes can be added to masked up entries in the page table that are not in use by the current process, as shown by example in figure 8.12 below. Note that the valid and invalid bytes described above cannot be blocked. All illegal memory access due to the internal fragmentation. Areas of memory in the last page that are not entirely filled by the process and may contain data left over by whoever used that frame last. Many processes do not use all of the page table available to them, particularly in modern systems with very large potential page tables, rather than waste memory by creating a full-size page table for every process. Some systems use a page table length register or PTLR to specify the length of the page table. Shared pages. Paging systems can make it very easy to share blocks of memory by simply duplicating page numbers in multiple page frames. This may be done with either code or data. If code is rentrant, that means that it does not write to change the code in any way. It is non-self-modifying, and it is therefore sought to re-enter it. More importantly, it means that code can be shared by multiple processes so long as each has their own copy of data and registers, including the instruction register. In an example below, three different users are running the data simultaneously, but the code is only loaded rather, into memory in the page frames one time. Some system also implement shared memory in this fashion.
In structure of the page table. Hierarchical paging. The most modern computer systems support local address space of 2 to 32 to 264 with a 232 address space and 40 to 12 page size. This leave 220 entries in the page table. At the bytest per entry, this amount to, to, to a 4 MB page table, which is too large or reasonably keep in contiguous memory and to swap in and out of memory, which with each process switch, not that which with 40 page this would take 1024 page just to hold the page table. One option is to use two tiny page system, i.e. to page the page table. For example, the 20 bytes described above could be broken down into two 10-bit page numbers. The first identifies an entry in the outer page table, which identifies where in memory to find one page of an inner page table. The second 10 bits finds a specific entry in that inner page table, which in turn identifies a particular frame in physical memory. The remaining 12 bits of the 32 bits look, local address are the offset within the 4 key frame. VAX architecture divides 32-bit addresses into 4 equal size sections, and each page is 512 bytes, leading an address from off. With a 64-bit local address space and 40 page, there are 56 bits, 52 bits worth of page number, which is still too many even for two level paging. One could increases the paging level, but with 10-bit page tables, it would take 7 level of indication, which would be prohibitively slow memory access. So some other approach must be used. Hashed page table, a common data structure for accessing data that is sparsely distributed over a broad range of possible values is with hash table figure 8.16 below in illustrates of a hashed page table using Chan and bracket hashing. Inverted page tables. Another approach is to use inverted page table instead of a table listing all of the pages for a particular processes. An inverted page table lists all of the page currently loaded in memory of all processes. IL, there is one entry per frame instead of one entry per page. Access to an invented page table can be slow, as it may, may, be, may be necessary to search the entire table in order to find the dis- described page to or discover that it is it is not there. Hashing the table can help speed up the search process. Invented page table prohibit the normal method of implementing shared memory, which is to multiply logical page to a common physical frame, because each frame is not mapped to one and only one process. Example, Intel 32 and 64-bit architectures optional. IA32 segmentation. The Pentium P CPU provides both pure segmentation with paging. In a later case, the CPU generates the logical address segment offset pair, which the segmentation and unit converts into the local inner address, which in turn is mapped to a physical frame by the paging unit as shown in Figure 8.21. IA segment 32 segmentation. A virtual architecture allows segments to be as large as 4 MB, 24 bits offset. Processes can have as many as 16,000 segments divided into 8,000 groups. 8,000 private to that particular process stored in the local descriptor table L or LDT. 8,000 shared among all processes stored in the global descriptor table or GPT. Logical addresses are selector offset pairs where the selector is made up of 16 bytes and 13-bit segments number up to 8,000. A A1 bit flag of 4 LDT or versus GDT 2 bytes for protection codes. The descriptor tables contain 8-byte descriptions of each segment including base and limits receptors. Logical inner addresses the general by looking the selector up in the descriptor table and adding the up, appropriate base address to the offset of shown in Figure 8.22. I-1 32 paging. Premium Pentium paging normally used to two-third paging stream with a first 10 bytes being a page number of for an outer page table, aka page directory, and the next 10 bytes being page number within one of the 1024 inner page table leaving the remaining 12 bits as an offset into a 4,000 page. A special bit in the page directory can indicate that this page is a 4 MB page, in which case remaining 22 bytes in are all used of offset, and the inner tier of page table is not used. That CR3 register points to, to the page directory for, for the current process as shown in page figure 8.32 below. If the inner page table is currently swapped out to dest, then the page directory will have an invalid byte set, and the remaining 31 bytes provide information on where to find the swapped out page table on the desk.